Hey, thanks for coming back for another boring video. As a matter of fact, this topic's kind of boring, but it's I guess like if I use my imagination, I can imagine a good animation, which I've never actually seen, of some of these collisions and reactions or non-reactions. The topic is collisions and how a chemical reaction hinges around particles colliding. Because if you think about it, how could particles interact, break old bonds, and form new bonds if they didn't, excuse me, come in close contact with each other? And not only that, some of the things that we think of and we measure and actually have verified when that interaction takes place. So, in any case, collisions are fast. Particles are moving at room temperature. Particles are moving hundreds or thousands of miles an hour and bumping into each other millions of times every second. So, I think you can use your imagination to envision that. I can, but take some practice perhaps. We imagine a reaction happening when the collisions occur, but not all collisions necessarily result in a chemical reaction, breaking old bonds, forming new bonds. For one thing, the collision has to be of sufficient energy. The particles must be moving, say, at a certain speed, or at a minimum speed. And not only that, they also have to collide in, sometimes at least, proper orientation. Molecules have geometries to them, and one geometry of collision, one orientation, might not lead to a reaction where another will. Number of collisions, collision frequency, the number of collisions that happen per second, and of course the warmer the substance is, the faster the particles are moving, and the faster particles moving, the more often they collide, the more likely there is to be a chemical reaction. More collisions, more effective, it lead to the formation of the products. That's what that says. This seems to me maybe a little bit randomish. I have a collection of slides I've used in the past. It's a blah 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 about collision theory and transition states. So the particles must collide. They must collide with enough energy in the right orientation. It's hard to believe we've actually verified in experiment and theorized with equations and theories about motions and how should I say distribution particles and distributions of speeds, how they will react, how frequently they collide, how they're oriented in space, and we actually have all these numbers. So you can forget about this slide because I'm not going to have you use the equation, but I just wanted to say it's amazing what we as humans, scientists, thinkers, experimenters have verified and observed with regards to these colliding particles. If I think about, here's an example, methane. If I just let methane escape from the natural gas jet from the Bunsen burner, it'll just enter into the air, and as long as no matches are lit, we're safe. But as soon as the match is lit, that match provides a spark or the activation energy to get that initial reaction going between methane and oxygen to create carbon dioxide and water in the combustion, releasing, let's see, is this a balanced equation? That's not even balanced. Oopsie. Well, anyways, I'd probably put a 2 here and a 2 here, yes, and that would balance it. Well, whoever typed this up, not me, made a mistake. In any case, I need something to get the party started, to get the reaction going. I need some activation energy. Not only that, they must collide, particles must collide in general with the right orientation. I might imagine if a diatomic X collides with a diatomic Y in either this orientation or this orientation or this orientation, they bounce off each other. Typically, nothing might happen. But I might also imagine then that if they collide with each other like linearly, like this orientation meets this orientation, then they will indeed form what we call an intermediate or transition state, and that means this bond weakens and this bond weakens and this bond forms and this bond forms, and voila, I have a chemical reaction. So the transition states, the intermediate, I don't know if I really shouldn't use the word intermediate, but it's some kind of in-between state that exists where old bonds are weakening and new bonds are forming. So imagine an ineffective collision, an effective collision. Perhaps if these two NOCl molecules collide with the two chlorines head on, that reacts, but a nitrogen and a chlorine, or two nitrogens, actually that's an oxygen. Oxygens wouldn't, this would not be effective in allowing a chemical reaction, but this would be effective. Interesting. This one's more blurry, but don't remember it. Just think about how it could be that this orientation of the N2O and the NO molecule would, if they collided like this, like the nitrogen on one, and colliding with the oxygen on the other end, might result in the transfer of an oxygen. Other orientations of the molecules wouldn't provide such probability, a likeliness of breaking old bonds, forming new bonds. And indeed, even in a collection of particles, we have some of the millions and millions of particles moving faster, and some millions and millions moving slower. Sometimes when you mix the reactants together, they'll naturally have enough energy just in the room thermal energy, temperature, to force the reaction. Sometimes you have to warm them up. Sometimes you have to add a spark or a fire to get them to go. But some particles move faster, some particles move slower. Good to think about. Here's a new term. An activated complex is an unstable chemical species that has old bonds breaking and new bonds forming. It indeed has been verified. They only last a few micro to nanoseconds, not even micro, like nanoseconds, sometimes even picoseconds. But they're kind of like the pathway from where I'm going to where I've been to where I'm going. Some kind of funky hybrid particle. Transition state theory postulates that high energy intermediates exist just for a brief time, and then they fall apart into the products. To get up over to create the intermediate, we got to get supplied the activation energy. This works all better with a bunch of pictures. Although I didn't type this one up, I'm using it sometimes. So if I want to get from here over to here, or from here even up to here, I have to get some activation energy into this boulder to get it up over the hill. It's sort of stable right here. This might be an intermediate that it hangs out for a while. But it wouldn't just stay there. It might even be pushed up over the hill further, or it might roll back down this way. So that's kind of a poor gravitational example from physics. But imagine the overall energy of the particles lower down here and higher up here, and I have reactants that are fairly high in energy here, and they collide with each other in this orientation. And if that's true, and if they have enough energy to get up over the activation energy, this is called free energy, or the overall summation of all energies contained within that sample. The G double dagger is the activation energy. Here's the delta G, or the delta E, or the delta. Sometimes we call it delta H because often heat's released, but to be more general, it's better, more proper to say the free energy. But in any case, this is the intermediate, the in-between thing, the transition state, where this bond is forming and this bond is weakening, and this thing won't stay here but a nanosecond. It somehow realizes that this state is more stable and lower in energy, so this collection will fall down the energy hill if given enough activation energy to create the products. Transition state. I like this picture. That's a good one. I don't know, this one, whatever. Again, if I have reactants higher in energy, the products are lower in energy. Somehow the reactants want to, I personify these things too much, they would desire to in some way get down to the less energetic state of XY. This is the activation energy, or the delta G, or the G double dagger, and the free energy, or the Gibbs free energy, the total amount of total energy content in these collections. Yeah, sometimes we can talk about the forwards or the backwards. So one diagram would summarize the forwards or the backwards. If I were going forwards, I'd supply a little bit of activation energy to get down to the products, reactants to products. And I would say this is exothermic, exoergic, or something like that, giving off energy. Thinking about the reverse, I could call these the reactants and these the products, and I would have to take these things and push them up over this energy hill. That's a big energy hill. And the delta E of the reverse is all the way from here to, did I label that correctly? I should have labeled that delta E or EA reverse. Anyways, it's going backwards. It takes a lot of energy to get up over that hill. But but even realize, do you realize in a collection of particles, some particles are moving faster and some are moving slower. We talked about this in General Chemistry 1 when we talked about distribution of speeds in gaseous samples. It also is, of course, true in liquids and solids. Some particles are moving faster and some particles are moving slower. Most particles are moving in the average speed. But if I warm things up, then that bumps many particles up over a certain level. That might be called the activation energy needed to get the party started. So warm reactions go faster than cold reactions because the particles are vibrating faster, they collide more frequently, they generally contain more energy, maybe enough activation energy to get over um, the bump, the activation energy barrier. So up here I might have some kind of transition state or intermediate. I don't know what that would look like, but it would have weaker new bonds and, weakening old bonds and strengthening new bonds. Again, this takes some activation energy, although we'll see there's a catalyst for this reaction. It's a very interesting catalyst. But if I had hydrogen gas and oxygen gas, I want to keep that mixture away from open flame unless I'm prepared to do it safely. Make sure nobody gets hurt and blows their eardrums out. Very exothermic. Sometimes that's nothing new. Well, this one's exothermic, yeah, and this one's endothermic because I start low and end up high. Endothermic reactions are very rare. Often we have to pump energy into them to get them to work. And as soon as we stop pumping energy in, then they stop creating the products. It's good to think about the difference between starting high and ending low, and this might be an exaggeration. Starting low and ending high. Curious. These are two separate different reactions, so C and D here are different than C and D here, and A and B here are probably different than A and B over here. Sometimes the bumps can be complicated looking, where the bumps here I just have one, maybe a catalyzed pathway. Oh, have we talked about catalysts yet? Have you thought about them? Dang, I forgot. Well, this video is not the topic of catalysts, so watch that video too. Anyway, I might have a transition state up here, high in energy, but it's not going to last long. It's either going to fall back down to where it came from, or realizing that the products would be lower, slightly lower in energy, they might fall down this way. I don't mean fall down like gravitationally fall down. I mean like energetically. The energy, somehow the particles, the collection, the intermediate realizes, the transition state realizes that it could be more stable by giving off more energy, and it'll do so. This is a biochem graph where I have a substrate and a product, a substrate and an enzyme and a product, and I might actually have one or two intermediates with one or two stable little dips in the middle. Enzymes are crazy. They're so complicated and amazing how they work. What else? One more thing? Two more things? Activation energy, activated complex, vocabulary. Oh yeah, so sometimes the transition state situation or the intermediate is also called the activated complex, where I have some intermediate ready to create products. Yeah, that's what I was saying. Activate chemical species with partially broken and partially formed bonds. This is a kind of a silly example of a isomerization, where this thing wiggles around and jiggles around and realizes that it might be more stable to have the carbon bonded to this carbon instead of the nitrogen bonded to this carbon. I'm sure it's temperature dependent, but it does happen. I suppose the weakening of this bond and the forming, the weakening of this bond and the forming of this bond between this carbon could be called an intermediate. But I like to go back to this picture when I'm thinking about weakening old bonds. Oh, too far. Darn, sorry. Oh, are you getting a headache yet watching this? Sorry about that. I went way too far. It's good there, right there. I like to think about this forming new bonds, strengthening new bonds, and weakening old bonds. And how would you know what's the old and what's the new unless you knew where it came from? Whew.